In this video, we will start by demonstrating the use of convolution for smoothing the uncertainties in experimental data which has a nonlinear response. We will then combine differentiation with smoothing to plot the variation in the slopes of experimental data. We start with experimental data with the x values in the first row and the y values in the second row, which are then plotted on this xy scatter plot. We will use a 5-point convolute with values -3, 12, 17, 12 and -3, whose values give a sum of 35. This sum will act as a normalizing value to ensure that the average effect of this convolute will have a unit value. The procedure in taking the convolute is then to multiply each convolute value, starting with G4, with its equivalent data value, in this case the y value in G2, and then add the equivalent product for the next convolute value in I4, multiplying by the equivalent data value in I2, and so on for all the other convolute values. And then we will use the value in Q4 as the normalizing value, so we will divide this by Q4. We need to put a bracket at the front. And because we're going to be copying this same formula to other columns without moving the convolute values, we will need to put a dollar sign in front of the column for each of the convolute values in row 4. So we will start with a dollar in front of G4, in front of H4, I4, etc. and also in front of Q4. So the effect now of multiplying each convolute value by its equivalent data value, adding them up and normalizing for the value of x equals 70 will give a value of 8.02. This value of 8.02 is the value at x equals 70 for a cubic curve which is the least square's best fit around these 5 data points. And we've recorded this as our best fit value, y dash, at the point x equals 70. We can now copy this calculation to the other data points just by dragging this formula along. Unfortunately, it's also copied some of the arrows that we have which impinge on this original cell, so we can get rid of these. And similarly, I will copy the calculation to the other cells on the left. Each of these points represents the best fit value for a new cubic curve fitted through the local set of 5 data points. Our best fit data points stop just 2 points short of each end due to the width of a 5-point convolute. We can now plot these values on the same XY graph as the original data by going to the graph and selecting data. We will add the new series of the x values over our range and then enter the best fit calculated values, and we can join these new data points with a smoothed line to get our best fit curve through the experimental data. We can also calculate the residuals at each of the data points. So in row 7, this is simply y minus y dash, which we can copy for all the other experimental data points. And then we can calculate the standard deviation by using the sample standard deviation function and highlighting the data range. to get a standard deviation of residuals of 0.244. We will now see how we can use a different convolute to carry out a differentiation of experimental data and to calculate the slopes within of experimental data. And the data we're using here is the results of a chemical titration, and we have values of x and y in columns A and B represented by the values on this graph. And the convolute we will use to calculate the slopes in this graph is given by this 7-point convolute in column C, again with a convolute sum given in C3. The calculation procedure is the same as the smoothing convolute in that we take the first convolute value and we multiply it by the equivalent data value, and then take the second convolute value multiplied by the second data value, and so on. This sum must then be divided by the normalizing convolute sum in C3. As we're going to copy this formula down to different rows, we have to lock the row values for convolute references. So we need a $sign in front of the 6 in C6 and in front of the 7 in C7 and so on, and also in front of the 3 in C3, and we can enter. But we have not yet completed the calculation for slope, because this value that we have here is the best fit estimate for the difference in y values between adjacent data points. And to get the slope, we have to divide this by the difference in x values between adjacent data points. And we can enter this in C2. The difference between x values is quite simply 0.5. So we will modify our calculation here by dividing by the difference in y values by the difference in x values in C2 to get the slope, and again with a $sign. So this gives us the slope of the curve at the point x equals 13.5. We can now copy this down to all the other relevant data values. We are now in a position to plot these slopes on this curve, but because of the difference in scale between the slope values and the y values, we will choose just to multiply the values of slope by 4 to make them more visible on the graph. So we will just multiply each of these values by 4 as a simple scale factor. And now we can add that data to our graph, and we can see here the values plotted for the slope of the graph at each point. And we can see clearly that the maximum slope occurs at a point between the x values of 20.0 and 20.5.